Today I'll talk about energy equation and CSTR with heat removal. CSTR with cooling coil. The CSTR system with a cooling coil inside the tank can remove the exothermic heat of the reaction, that is BTU per pound mole of A reacted or calorie per gram mole of A reacted. Now here heat generation is negative. Heat generation is negative for an exothermic reaction and positive for an endothermic reaction. So remember, heat generation is negative for exothermic reaction and positive endothermic reaction. The rate of heat generation Qg due to the reaction is the rate of consumption of A times lambda. So Qg is minus lambda into the rate of the reaction. So this is rate and lambda is the heat generation. So here the rate of heat generation Qg is due to the reaction is the rate of consumption of A times lambda. Now minus means exothermic and positive means endothermic. Now here lambda heat of reaction, energy per mole, V is the volume of the reactor, and Ca is the concentration of the reactant A, and K is the reaction rate constant. Now here if you see, this is the CSTR. Now reactant is coming to the CSTR. So Fa0 is the volumetric flow rate, ρ0 is the density of that inlet fluid, and Ca0 is the concentration of the reactant A at the inlet, and T0 is the temperature of that inlet fluid. Now the reaction is happening inside the reactor, so that is A to B, that is first order reaction. This is first order reaction, and this reaction is exothermic reaction. So for that cooling coil is inside that CSTR. From that cooling coil heat is actually removed. So now, and this is the outlet. At outlet outlet volumetric flow rate is F, density is rho, and concentration of that reactant A is Ca, and T is the outlet temperature. Now here we are going to do that energy balance equation in that CSTR. Now general energy equation. So the first law of thermodynamics for an open system is expressed as flow of internal kinetic and potential energy into the system by convection or diffusion plus heat added to the system by conduction, radiation and reaction. Flow of internal kinetic and potential energy out of the system by convection and diffusion minus work done by the system on surrounding, that is shaft work and PV work, is equal to time rate of change of internal kinetic and potential energy inside the system. Now here I am taking all this type of energy, and then I'll write everything, and then I'll ignore what is required. What is required, that will I'll take that, and what is not required I'll ignore that. Now here, so first flow energy into the system, so that will be F0 ρ0, so that is mass flow rate into internal energy, kinetic energy and potential energy. Flow energy out of the system minus Fp, that is again volumetric flow rate, and rho mass flow rate, that U plus K plus phi. Now heat added to the system, so one is sometime we add in externally, so that is Q0, and Qg, this is Qg is the that heat generation inside due to the reaction, and work done by the system, that is minus W plus Fp, that is P is pressure, minus F0 and P0, and rate of change of energy inside the system d dt of U plus K plus phi into that V into rho mass. Now here, so apply the general energy equation to the CSTR. So this is inlet energy, so all type of energy, the internal energy, kinetic energy, potential energy, then outlet the energy, that mass flow rate into internal kinetic and potential, then Qg plus Q0, okay, and then so that is either we are putting external energy or energy due to the exothermic reaction, and then minus that shaft work and PV work W into Fp and F0p, and then the rate of change of the energy ddt of U plus K plus phi into V into rho. Now here, so previous figure, okay, we assume no shaft work, that is W is 0, no shaft work, kinetic energy is actually 0, okay, negligible kinetic energy is 0, and negligible potential energy, that is also 0, so that is 0, okay, so that is 0. Now after that we have, so simplify that, so we will have something like ddt of, so here ddt of this U V rho, so ddt of rho Vu, and then inlet energy, so that is F0 rho 0 into U0 minus F rho U Qg plus Q0 minus F, that P by rho, so that is nothing but 1 by rho, means the specific volume, F0 P0 by 1 by rho 0, again 1 by rho 0 is specific volume, so PV work, so this and this. So U is the internal energy per unit mass, K is the kinetic energy per unit mass, phi is potential energy per unit mass, Q is heat added to the system, P is the pressure of the system, P0 pressure of the feed stream. Now after that, so we can further simplify. So here, so V is 1 by rho, so we put all this, okay. So now here, so F0 rho 0, so in that this side F0 rho 0 U0, and here that is 1 by P0 is nothing but specific volume V0. So now if I take the common F0, then it will be like a F0 rho 0 U0 plus P0 V0 minus Fp U plus PV plus Qg and Q. Now we know that enthalpy H is equal to U plus PV. Now we can put that H. So if you plug this, so ddt of rho V into H is equal to, so here U plus PV, so here that PV is 0 in this case, so we can plug that here. So ddt of PVH is equal to P0 rho 0 H0 minus F rho H plus Q, that is the external energy, minus that is the energy generation. So now energy generation, the enthalpies are the function of the composition, temperature and pressure, but are primarily influenced by temperature. Now we know that Cp is equal to dou H by dou T, Cv is equal to dou U by dou T. Now from here, so we can write H is equal to Cpt. Okay, so now if I plug that, so that will be rho Cp ddt of Vt. Okay, so here we plug that H is equal to Cpt, so here H is equal to Cpt. So from we can easily here V and T is actually that variable, so rho Cp common, ddt of Vt is equal to rho Cp F0 T0 minus Ft plus Q minus lambda Vk Ca. Now here lambda, we know the lambda is negative because the reaction release heat including the internal energy of the system, and endothermic reaction lambda will be positive. So I told you, so that indicating that heat is absorbed in increasing the internal energy. Now finally we'll get that final simplified equation, the final form of the energy equation of the CSTR with heat removal, rho Cp ddt of Vt is equal to rho Cp F0 T0 minus Ft plus Q minus lambda Vk Ca. So this is for first order reaction. So this equation captured the balance between heat input, heat output and the heat generation by the reaction. So this is the heat energy equation for the CSTR with heat removal. So that's it. Thank you.